Good. And the chat. So most of you realized that last week that we didn't have a class. The circle of people who realized that didn't involve me, because I did show up for class, waiting for everybody else, and there's only one other person showed up, and then we together concluded before the third person joined that there was no class last week anyway, sir. But most of you did realize it, so that's a plus. For that reason, because I didn't do anything I did do things last week, but not in the class. I didn't cover the material as I was planning, so I miscalculated what I would cover, so that's why I extended the deadline for the homework. So it's due next week, and I fully hope to cover whatever I ended up not covering. Let me remind you what we did last time. I just need some more light, just 1 second. Okay, so we were talking about stability of Hamiltonian systems in the most general case. How far should I go back? You might remember that the general problem was that, okay, 100%, that when you have a autonomous Hamiltonian system, that was our setting. We knew, we had concluded that if the Hamiltonian has a minimum or maximum, then immediately at the origin, then immediately the Hamiltonian serves as a Lyapunov function. You can conclude the stability of the origin. So basically, whenever the Hessian of the Hamiltonian is definite, then you immediately have stability, no questions asked. A problem arises when it's not definite, so when it's indefinite. And I mentioned one example is a gyroscope, you might remember, the tippy top, for which the potential energy has a maximum there at this upright equilibrium at which the tippy top spins when you spin it up fast enough. So that it has a maximum, cannot grow any larger, but the kinetic energy certainly grow larger, because at this point, these positional or essential coordinates that measure your displacement from the relative equilibrium, they are at standstill. There's no kinetic energy content to those radial directions. You can really hit it hard and you can drive on the kinetic energy as much as you can, the relative kinetic energy, because the spinning is excluded. So that's just kind of the physical example to keep in mind, that the systems that rotate relative to each other and have relative equilibria have this configuration that the Hamiltonian is indefinite. So we wanted to look into that. And as I indicated last time, there was a very, very, still actually active area in nonlinear dynamics to understand that case. And you'll see shortly why it's so complicated. But back to that, the first step was we linearized the Hamiltonian at such a fixed point where we do not, I made no assumption that this is definite. What I'm doing for now is actually valid, generally speaking. And the new local coordinates were y, right? And the linearized part, the linearized system was Hamiltonian also, we noted that before. So we can do a canonical change of coordinates. Canonical change of coordinates that is a change of coordinates that preserves the Hamiltonian structure, meaning that if you perform this change of coordinates, then you preserve the Hamiltonian for yourself, so that even after the change of coordinates, the Hamiltonian will keep acting as a Hamiltonian. So that's a big advantage in Hamiltonian dynamics, that if you're able to change coordinates in a canonical way, as they say, then it's enough to do your manipulations on the Hamiltonian itself, rather than having to carry potentially, 1,000 differential equations. It's enough to do the change of coordinates on the Hamiltonian, which is the scalar function. Okay, like I said, I'm not going to go into what the canonical transformation is, but I give you a reference. It's not a big deal, but it's a bit algebraic, so we don't need it, strictly speaking, here. So this would be your linearized Hamiltonian, and the assumption was that the roots were purely imaginary, okay, at the equilibrium point, so you don't have any definitive stability type. And I organized then the roots, assuming that the linear part is semi-simple, which means that I can transform the system into this Jordan canonical form in which I have these boxes, right? Skew symmetric ones, sort of the best form, real form you can get when you have a purely imaginary eigenvalues. But this omega j's may be positive or may be negative. If all of them are positive up here, if you can achieve that, then it's a definite Hamiltonian. But I'm not assuming that. So all these can be positive or negative. We discussed a little bit the dynamics then, what ensues or what becomes visible in these coordinates. These are rotations. The individual dynamics in each and every degree of freedom, there's n of those, is governed by these types of differential equations. We've seen that. So just look at what they are. They're basically little two-dimensional ODEs with a skew symmetric coefficient matrix. So those are centered type fixed points when you do the analysis quickly. So you can put together the whole dynamics just by looking at these little, essentially decoupled linear oscillators, right? And imagining that the resulting motion, since all of them are independent of each other, you can put together resulting motion by taking the topological product of circles. You place yourself on this, in this oscillator in this circle, in an intermediate oscillator with another circle, and in the final one yet another circle. Then each and every projection will be confined to its own circle. So when you try to represent that in the full phase space, you'll be taking the product of these circles, and the product of circles is topologically an n-dimensional torus. So all motions take place on an n-dimensional torus, and at least that explains that for the linear system, remember, we were wondering what would keep you here when your Hamiltonian is indefinite. So basically, this is the shape of your Hamiltonian rather than having a cup shape, in which case, you know, you will be confined to an energy sphere. Here, you're on energy surfaces that are opened up, right? So there's nothing that would keep you there. And this is the reason why you're staying there in the linear system. The topological reason is that you're confined to these, you know, n-dimensional tori that look like this, and you're doing motion on them. We talked a little bit about so the whole phase space, as we say, is foliated by these invariant tori, n-dimensional invariant tori. When n is equal to 1, then it's just a circle, then you have a two-dimensional torus, and so on. And I spent a little bit of time about explaining what type of motions you can have on the tori. If these omega i's, the frequencies, are rationally independent, then each and every trajectory is actually dense on the torus. Rational independence means that you can only generate a zero linear, integer linear combination out of the frequencies if the integer vector that you put into that combination is identically zero. So in other words, you can only force these to vanish in an integer linear combination if the integer linear combination is trivial, and it would force anybody to vanish because it's identically zero. So in that case, we say that they are rationally independent of each other. If however, at least some of them are dependent, then you will find non-trivial combinations, integer combinations that vanish. Okay, and in that case, you will not have a dense orbit, and you can have two different behaviors. You may still have dense orbits on a lower dimensional torus, but then the larger torus would be foliated by these lower dimensional tori, and those tori don't talk to each other, meaning that you're confined to a lower dimensional torus, but you will never be dense on the full torus. Or you have full resonance, so all of these are rationally related to each other. There's an integer linear combination involving all of them. There will be actually a closed orbit going back. Okay, and these you can actually verify, and I was sort of hesitating how to write this out, by introducing polar coordinates, because that was going to be the next thing that I was going to do anyway. So it's very beneficial to look at these systems in terms of canonical polar coordinates, which are like normal polar coordinates, but somewhat different, so that they keep the Hamiltonian structure. So the canonical, this is too thick, this is too thin, bring it down. So you introduce canonical, what we call canonical polar coordinates. And the pairs of variables are yj and yj plus 1 that are currently canonically conjugated. So you write yj equals square root 2 rj, this will be the polar length, times cosine phi j, and yj plus 1 is minus 2 rj square root sine phi j. And you might ask, why don't I just let rj cosine phi j, rj sine phi j, which is the usual polar coordinate transformation that you execute when you have rotational motion, you would like to understand that. And that's a perfectly legitimate question. And the answer is that is the canonical. So if you do it this way, if you don't go with the usual polar coordinates, but you do this type of transformation, then you will keep the canonical structure. For those of you who are just about this mysterious canonical thing, I don't want to go into differential geometry, but if you know a little bit about differential forms, then the requirement should be when you change coordinates for the coordinate change to be canonical, is that pairwise canonical, is that if you take this differential form, so the differential of yj with the wedge product of that, should be equal to the same wedge product in the new set of coordinates. Okay, but I don't want to go into that. In fact, this has to hold for the sum of all of them. But if it holds pairwise, then it's already a canonical change of coordinate. So generally speaking, that's what has to be respected in a canonical transformation. And if that is respected, then it's enough to work with the Hamiltonian, which is a huge benefit because you don't have to do the transformation on the equations. You just do it on the Hamiltonian, and then you rederive the equations, and it will check out. If it's not canonical, it will not check out. You do the transformation on the Hamiltonian, and you again derive the Hamiltonian equations of motion. They will not be corresponding in any way to the original Hamiltonian. So that will be a different system. So that's why one has to be careful here. But again, that's something you can look up, and it's a bit too algebraic. I'm not going to go into that. So in terms of these coordinates, because it's canonical, I can execute the coordinate change on the Hamiltonian. And when I take the linear Hamiltonian, so the linear Hamiltonian, the new coordinates, and the linear Hamiltonian, the old coordinates I've written out somewhere, presumably. Did I? So the hj, which would have been, if I'm not mistaken, hj equals 1/2 omega j yj squared plus y. Need more space. So hj equals 1/2 omega j times yj squared plus yj1 squared. And the full Hamiltonian is just the sum of these. If I do a quick derivation, then to check this, right, then I would have to take the partial derivative of this hj with respect to j plus 1. So that seems to check out for this one. And then I have to take the negative partial with respect to hj, so that checks out. So this was in these original coordinates, this was the Hamiltonian. Now you can take this coordinate change and simply plug it into that Hamiltonian, okay? And if you do so, you will be, squaring these variables. So you will get 2rj cosine squared, and then you get 2rj sine squared. So when you add them up, you simply get 2rj, right? But then you had a 1/2 that cancels out. So very conveniently, the individual Hamiltonians, the jth corresponding to the oscillator is just omega j rj. So no dependence on phi. So basically with this, you have removed the dependence. The full Hamiltonian is still the sum of these individual ones, right? So basically it only depends on the polar coordinate. And the dynamics in these coordinates before I do anything, just the linear dynamics, still the linear, just restates what we had before in another way. So it would say Rj equals 0. So the polar radius is not changing in time, and the phi j dot equals omega j. And again, the way you get this, this would be the negative partial of h with respect to phi j, but there's no dependence on phi j, right? That's why it's 0. And then this would be the partial of h with respect to Rj. Okay, and that just reproduces what I said before. Now I'm writing this out, this form, because this is the form which is advantageous for further analysis, it turns out. So you can take this Hamiltonian, work only with the Hamiltonian, and apply a near identity change of coordinates to bring it to normal forms, to its normal form. The normal form of a dynamical system near a fixed point is something we discussed in the last semester. It's a near identity change of coordinates that simplifies the dynamical system, a polynomial expansion of that dynamical system near the equilibrium as much as possible. So you basically expand the right-hand side near a fixed point, and you seek a near identity change of coordinates. So identity plus higher order terms, this idea is due to Poincare, such that you would knock out as many terms in the Taylor series expansions as you can. It turns out that very often there are terms you cannot knock out. Those are called resonant terms. The exact same thing can be done for Hamiltonian systems, of course. However, it can be lifted up to the level of the Hamiltonian itself. So you don't have to mess with the equations and do this, vectorial transformation and try to see what polynomial terms you can knock out in 100 equations or 2,000 equations. The beauty of Hamiltonian systems is that you can perform this operation in the Hamiltonian itself. So you Taylor expand the Hamiltonian near your fixed point as a polynomial. Once it's in polynomial form, you can introduce these polar coordinates, right? So it will become then a polar nonlinear form with powers of r and sines and cosines and the like. And then you may seek a near identity transformation, identity plus expansions against small terms that will knock out as many terms of this Hamiltonian as possible. Okay, it's the exact same theory, except that it's simpler in the sense that you're executing it on a scalar valued function rather than on a vector valued thing. But so I'm not going to go into that. The idea is the same. I'll just give you the results. So perform a near identity change. Of coordinates. To bring now the full, because this was the linearized. So basically what you would work with is that you would have these coordinates phi and r, and you change to say phi tilde and r tilde, which are very close to this one. They only differ in polynomial expansions of x and y. So those will be still, they will be periodic in phi. You will have cosines phis and sine phis, various powers of those, but they will be polynomials in this variable. Okay, so that's the same type of normal form that we did in the first semester. So it turns out that this is doable in the following. So this is doable up to cubic order or a quartic order. Under the non-resonance condition, which looks like this, is the type of non-resonance condition we've been discussing, that I'm taking integer linear combinations of the frequency vector, and I want non-resonance. So I want this to be non-zero, Okay, so I'm focusing on Hamiltonian equilibria that don't have an obvious resonance, a strong resonance, a strong one, that is, because I'm only requiring this for low order k's. So the k norm, which is a type of norm that we have for integer vectors in this theory. So this is taken from Zn, but I don't care. I don't want to allow 0, because if I allow 0, then clearly this is 0. So the length of that integer vector, which I measure by just summing up the norm of its components, okay, I require that to be less than or equal to 4. So I want no resonance among the eigenvalues of the Hamiltonian, but not up to any orders, only up to this order. Okay, so if you have a resonance that you can say one of these imaginary parts is a large prime number times the other one. I can't. What's a large prime number? When it doesn't even have to be that large, right? 13. One of these 13 times the other. That's okay. It's just that it cannot be a low order resonance. So it cannot be a 1 to 2, 1 to 3, and so on. None of these strong resonances. Then under this condition, actually the normal form for the full Hamiltonian, and I should distinguish that. I mean, this is let's call this the sort of the linear Hamiltonian. That's the linearized Hamiltonian, so that we don't have a conflicting notation. Okay, so L here means linearized. Remember, I'm only looking at the linear dynamics at this point, but the whole Hamiltonian, of course, originally is nonlinear. So that if I want to relate the two, then there will be higher order terms here once I've introduced this change of coordinates. So I will go through I apply the same change of coordinates that I have done so far for the full nonlinear system. And then first to the y coordinates and then to the r phi coordinates. And then I do this normal form transformation for the full system to obtain the following normal form to this assumption. So H, which is the new changed variables, so drop tilde, is what I had at leading order. It's omega j rj. I'm not changing that. That's the linear part of the system, and this is a nonlinear change of coordinates, starting with the quadratic terms. So it doesn't affect the linear part of the Hamiltonian. That was also the trick we used for classic normal forms, that we started with nonlinear terms. We didn't add a linear part to the change of coordinates, so that we leave the linear part, which was already nice, unaffected. So that's that. But here comes the non-trivial part. So even if you require these non-resonance conditions to hold, right, even then there will be parts of the Hamiltonian that you cannot remove. And that part will be like this. It's terms omega kl, these are real numbers, r to the k, sorry, not r to the k, that would make much sense, rk, the kth polar radius, and the lth polar radius. Okay, and here these are second order terms. So that's what you see here, second order terms, and the index goes, kl goes from 1 to n, plus order, the next term is r to the 4th. So what are we looking at? The normal form is the linear Hamiltonian, which we have analyzed already here, right? This is the phase portrait of the linearized Hamiltonian system, what you see here. I'm just showing it now in polar coordinates. This is linear. I do have quadratic terms, so that's just the nature of the eigenvalue configuration, that there will be, so to speak, natural resonances between omega and its conjugate. And when you plug that into the normal form transformation, which say when you execute that in a polar context, complex context, then there will be simply terms that you cannot remove. However, you're still doing much better than you normally would, because at this order, you would normally have phi dependence already. And you didn't have phi dependence here, but if you didn't do a normal for transformation, the phi dependence would already start here, and you would have a messy situation here with cosines and sines of phi, which would ultimately couple the equations. However, the normal form transformation was able to remove the phi dependence here, and at least you just have R dependence, nothing else. And all the coupling between the R and phi coordinates is here. So the phi dependence has been pushed to higher orders. And that has a big advantage, because that means that the normal form, the normalized dynamics is still simple. So let's see, R dot, remember what that is. R dot is the negative partial of H with respect to phi. That gives you 0 in the linear system, right here. And it's still almost 0 because there's no phi dependence here and there's no phi dependence here. So the first dependence on phi comes in somewhere here, and that's order R to the 4th. The phi dot, which is the partial of H with respect to R, and I should have J indices here. Well, understand these as vectors, okay? Then what is that? Well, here's my Hamiltonian. If you think of this as a vector, then what you see here, the R as a vector and omega as a vector, then what you see here is R dot omega, right? So these are vectors. So this derivative will simply be then omega, the frequency vector. And when you take the derivative of the next term, which is quadratic in R, you take the derivative of that in R, then you get a term which is linear in R, but it still only depends on R. So this is order R. Okay. And then you have the higher order terms. Let me push this a little bit further here. So the advantage is that up to this order, and this is now the nonlinear system, we still have a decoupling between the two degrees of freedom, or two sets of degrees of freedom, right? So R is, remember, is an n-dimensional polar variable, plus, but also 0 is fine. It cannot be negative because it makes no sense. And phi is then taken from the n-dimensional torus. And these two equations still decouple from each other. What does it tell you? It tells you that after you've made this nonlinear change of coordinates, you have demystified part of the nonlinearity, because you can, in the appropriate coordinates, remove the phi dependence, push it to high order. So even part of the nonlinear system behaves like the linear system. Why? Because there's no change in the polar angle. So you basically are still running in circles in each and every degree of freedom. It's only your angular velocity that is now modulated by a small amount, but it's still close to the omega frequency that you had before. So even at leading order approximation, when you start taking nonlinearities into account, in the appropriate coordinates, you are pretty much still here, right? So I'm already have added some of the nonlinearities. They're here, and by changing coordinates, I'm able to reproduce the toroidal dynamics. The only difference is that I have now modulated velocities on these, right? They're not uniformly rotating. They're modulated by a small term, but they're still going around, okay? That small term, although it doesn't change the existence of these invariant tori, it will change immediately the internal dynamics, right? So what used to be a resonant torus or non-resonant torus, that was a delicate balance anyway, right? Because, you know, I can find rational numbers arbitrarily close to irrational numbers and vice versa. So that is now changed by this term here. And depending on how far you are from the origin, that fundamental linear frequencies will be changing, you know, on the tori. Okay, but at this leading order approximation, so you now have frequency, you still have invariant tori, so up to order 3, up to cubic order. Motion is still on invariant tori. Note that in the original coordinates, these tori are now slightly deformed, right? Because I get the standard tori after this near identity change of coordinates, but when I go back to my original coordinates, they will be deformed. So they're slightly, you know, bumped, crooked, but they're still invariant tori. All motions are of them, but the frequency is now modulated. Okay, so fundamentally, you still have this picture for each and every motion. The only thing is that on individual tori, who knows what exactly happens? So the torus itself is there. So this is still n-dimensional torus near the origin. Who knows what exactly happens? So that makes us optimistic, right? Because they'll say, okay, under this non-resonance condition, I was able to uncouple the two systems up to this order and make this conclusion. Now it turns out that if you then have a higher non-resonance condition, then you're able to push this bar further, and you can still uncouple the two systems from each other, because your normal form transformation, although it will not be able to remove each and every term, just like this one couldn't either, but it will be able to clean up these terms from their phi dependence and push the phi dependence to higher orders, right? So I can just, you know, assume higher and higher and higher non-resonance conditions and march along, right, and do this. At the same time, that non-resonance statement becomes kind of a formality, because as far as the actual motion is considered, I will have more and more corrections to that here. So what actually takes place on the tori is far from what starts getting far from what the linear dynamics was doing. So I think people are very optimistic that you can push this, you know, to infinity and ultimately find that each and every motion is moving on an invariant torus. However, that doesn't turn out to be the case. This is one of those classic examples that people like to ignore, and when they do perturbation calculations in practice, and they say, if I see something at leading order, I'm sure it's there. This is the classic counterexample. No, it turns out that you can still save many of these tori, but not all of them. A lot of them, infinitely many, will be destroyed when you try to push this procedure to infinity. The following is the big result here, which is the question that I want to answer: what happens to these tori under successive under higher order normal form transformations? And the answer bears several people's name. It goes by the name of KM theory, which stands for Kolmogorov, Arnold, and Moser, which was a fantastic achievement. Kolmogorov was a Russian mathematician who basically sketched his main ideas as to what will happen when you add those high order terms. He didn't work out the details. As far as the details, his student Arnold, who was also a fantastic mathematician, worked out at least most of the details, but he got results that required some conditions like 333 times differentiability or something like that, which seemed unnatural. So he had a very specific, I think it was 300 if I'm not mistaken, but he got results under the assumption, let's assume that the Hamiltonian is X many times differentiable, but that was sort of a Y 333 or whatever. And at the same time, Jürgen Moser, who was originally from East Germany, I think, and then ended up in the United States and became very famous there, showed how that can be removed, that differentiability requirement, and that required very serious additions to the original theory. And that's why, even though he was showing it first on the lowest possible dimensional case, not in the n-dimensional case, his contribution is very much important there. So this is the KM theory. It's a celebrated result, and basically says the following, that assume that the above limited non-resonance condition, let's call it star, holds. So in other words, the first step is what I have outlined here is doable. So you can in fact get to this normal form. Otherwise, there would still be coupling here at leading order. Here, I could not achieve this cleaning up from phi if I didn't have the non-resonance condition, but under the non-resonance condition, this is okay. So assume that your equilibrium point, the frequencies of that are not strongly resonant, and there's a non-degeneracy condition also, that the determinant of this matrix, coefficient matrix, omega KL, is non-zero. So basically, when you look at this, which I haven't written out, when you look at the frequency correction that comes out of this, and I should actually write this out to make this more understandable. I apologize, I make that just more specific. Right? This is a quadratic form, and you have to take this derivative with respect to R here. So when you do that, then you in fact get this omega KL matrix acting on R. So that mysterious term that I didn't write out is just that. I think the next one is R cubed. No, R to the fourth, that's 2. No, that's fine, because you differentiate R to the fourth and it comes R to the cube, right? So this is that correction term. And basically, the intuition for this condition that you see here is the following. It basically ensures that the resulting frequency variations after this modulation are still diverse enough. Because if this matrix has full rank, then if you start exploring, in various directions how the frequency is modulated, you will be getting all sorts of values. So that means that as you're moving away from the origin, yes, you might be, what used to be a non-resonant torus at the origin, which turns out to be the nice thing, the robust thing, because you're covering it densely. It might get changed immediately for certain values of R into a resonant torus all the time, right? But you still have a lot of diversity. You will still have a lot of non-resonant tori as well, because this mapping here, that this part of the mapping that maps you from position place to frequency space is non-degenerate. So it will have a full range. That's the intuition behind this. So that part it gives you a rich enough set of tori with all sorts of frequencies. And the statement is that if you take that rich enough set of tori and now you add the perturbation, then even though a lot of them will still be killed off, many of them, and in fact the majority of them, will survive in a deformed form. And that was a very hard statement to prove. That was the first kind of topological statement of the type in this area. Most of it survives. And here's the statement. Then most, I'll just, instead of epsilon statements, then most invariant tori, the term is, which I used before, I think, persist, which means that deforms but survives. in the full Hamiltonian, at least close enough to the origin. So if I want to get a little epsilonish about this, then this will, mu will be the measure. And in this case, the Lebesgue measure, one cannot use volume because we will be talking about things that are not necessarily open. So it's really, it requires a bit of, which I can't go into here, but some sort of intuition for measure at least, or prior studies, but it's something more general than the volume. I used the term measure before. So the measure of the surviving tori in a B epsilon ball. So imagine a little ball that you take around the zero equilibrium point. So this is y equals 0, okay? And I take a little ball. So this is B epsilon, whose radius is epsilon. So the statement is that there will be surviving tori within that ball, many of them. But the torus is still a two-dimensional surface. So whichever way I tweak it, a three-dimensional, or not two-dimensional surface, my picture, an n-dimensional surface in a 2n-dimensional space. So this measure mu is a reasonable measure on the 2n-dimensional space, with respect to which a lower dimensional surface will always have 0 measures. So an individual torus will have easily 0 measure, no question. But there's so many of them. There's such an, in fact, a Cantor set of them, it turns out, that they occur with such density that when you add all that up and divide this by the measure of the ball itself, which will be just the usual volume, and then you take epsilon to 0. In other words, you try to find the relative measure of surviving tori in this ball, and you're willing to take the ball smaller and smaller. And this is actually 1. So full measure. So that's the most, that's the statement here. So that was really a fascinating statement to obtain. People were hoping that all of them survive, but in fact, infinitely many are killed off. But the ones that survive are still in a deformed form, are so dense that if you add up their appropriate measure, then even though individually they have 0 measure, and nobody says that they will form an open set ever, but they're just so dense that they're approaching full measure. So this is a remarkable statement and required completely new techniques to prove. So this is part of the statement. This is a whole theory, there are twists on this for various systems, even for partial differential equations. There's an infinite dimensional version of the KM theory, which is about the partial differential equations. What happened that are, many of them can be viewed as Hamiltonian dynamical systems. And look at the linearization, they have a particular stability type, but in an infinite dimensional space. And what happens when you add the nonlinearities? So that theory is hairy, so it's more complicated than this one, but even has an extension to infinite dimensions. So the surviving tori are quasi-periodic. And with the reduced dynamics R dot equals, it starts with a 4th order term, but it depends on phi, as we said before, and then you have phi dot equals some omega tilde R phi. And remember, that was just omega plus this omega KL matrix plus, times R plus order R cubed. In fact, if you really want to, although this is a Cantor set typically, so it's not a connected set, you can introduce a smooth coordinate nevertheless, that on the surviving tori, that polar variation will be 0 exactly, not just r to the 4th, but 0. So basically you're introducing yet another set of coordinates in which the torus again becomes completely circular, right? But that's not so important at this point. And there comes an additional modification, which I think that I personally didn't understand the significance of that as I was, learning about this. I think as a master's student, and the next one just seemed like an overkill, but it's not. It's actually very important, and it's the following. So and you'll see in a second why. Under the additional, what's called isoenergetic non-degeneracy. So this is yet another, we already had a non-degeneracy condition. Remember that this frequency modulation here, the frequency distribution had to be rich enough. So then this matrix had to be non-singular. Now this one is not so easy to explain, but its implication will be easy to explain. So the additional isoenergetic non-degeneracy condition, which has this form, omega KL, the same matrix, okay, but now I do the following. I add omega here, which is a column vector, an n-dimensional vector. So its dimension in this direction matches with the dimension of that matrix, so I can do that. And now I also add omega here, but it's transposed. So since it's an n-dimensional vector, then in this direction, its dimension will match with that direction. So all I need to do is just add the 0 here for this to be a square matrix. And now I require this to have non-zero determinant. Okay, and it's called isoenergetic non-degeneracy condition. And you will see why it's called that way, because we also, so under that condition, most tori, most again in this measure theoretic sense, survive on each energy surface. So not only do they survive in a neighborhood of the origin, most of them, but also if you just restrict your attention to a single energy level set, then within that they survive. Why would you restrict yourself to a single energy level set? Because for any initial condition, when you try to explore where it goes, that's in fact, it only sees that, right? It cannot go to any other energy level because this is a Hamiltonian system. So when you try to study escape or lack thereof, it's enough to pay attention to the energy surface. Am I being bounded within the energy surface? Am I not being bounded? Remember, we are in the general context where we have not assumed that we are being bounded. So we are in this case. So we are really trying to see if there's anything still that blocks me here or there. And now you could say at this point, which I did also think, like I said earlier, when I first heard this, that, hey, we already have that, right? Because, hey, most of the tori survive, right? So there's tori everywhere, right? Here. But think about the statement most. Most means that all except for measure 1. In fact, that's not even true here, that because almost all would be that. Most is different. Look, I didn't say that this quotient here is 1. I said that that it tends to 1 as epsilon goes to 0. So when epsilon is non-zero, so I'm at some finite distance, it's not 1. So there are gaps among the tori. But they are getting smaller and smaller as you get closer and closer to the origin, right? So there are gaps. Now, for all I know, if this is a measure theoretic statement that says, you know what, the tori that survive have a large measure. Essentially, that's a large relative measure. If that's all I can say, then who's to say that there is not a full energy surface on which all tori are killed off, or 2, or 3, or 4, right? because those are just individual surfaces that have measure 0 that would not affect in any way my statement. However, that would be a major problem when I could talk about stability, because there could be energy surfaces in which all barriers are completely removed. So high in certain energy levels, I could escape for all I know just fine. So that's why the original KAM, when you start talking about stability and possibility of escape, is not strong enough. It has to be made stronger, and that's why this isoenergetic non-degeneracy, which is due to Arnold, is a step towards that, because it tells you that, just check this additional condition, and then if that is whole, then you in fact can make this statement that I have just made relative to each and every energy surface, not just relative to a full neighborhood of the equilibrium. In other words, you can restrict to an energy surface, take a sphere within that, and repeat the same statement. So that's very important. So as you'll see in a second, the picture that goes with this is here's somewhere the equilibrium point, and say here's an energy surface nearby. It doesn't necessarily go through the equilibrium point, but it's also not necessarily a sphere because we're in the general context. So the way to imagine things now is that I can, if I take a large sphere, which I have in the original KM statement, I mean large, in fact, a small sphere, so this would be B epsilon, right? Then once again, the original statement says that most of the tori survive, here and there, everywhere, but I could still sneak out along this particular energy surface because that still has just very small effect 0, measure 0. So what the revised, or this, sharpened statement says that, essentially you can intersect this energy surface with this sphere, and that gives you a lower dimensional sphere. Let me try to do justice to that. So this is the intersection of B epsilon with the energy surface. So this is where Hx equals H naught, to be specific, which is just E H naught, the energy surface. And now I can make the statement relative to that if I consider now this lower dimensional sphere, okay, then even within that sphere, I have most of the tori surviving. Okay, and we'll see whether that, so these will be most tori survive here. But not almost all. That's important. Not almost all, most of them. All right, in terms of measure theoretically, most of them. And you get closer and closer to the almost all as you're willing to shrink the size of the ball. All right. So now, why have I gone through this? The big question is still stability. So what are the implications for stability? Of the equilibrium. That's why we did the whole thing. So one thing to know before we go into that, that in the general context that I'm looking at, the dimension of the torus is n, because we had n frequencies, right? And the dimension of the energy surface, any energy surface, is what? Well, it's one less than the dimension of the full phase space, right? If it's a nice energy surface, it's a nice codimensional one manifold, which I'm assuming nearby. So it's 2n minus 1. So a result of that, what we say the codimension of the torus is 2n minus 1, which is the dimension of the energy, I didn't finish the sentence, codimension of the torus within the energy surface. Is the following. I take the dimension of the energy surface, right? And I subtract the dimension of the torus. So that's n minus 1. And just something to keep in mind at this point. So specifically, let's start from what the implications of that for n equals 1. So when I have a 1 degree of freedom Hamiltonian, what does this general result give me? Well, if I have n equals 1 for the degree of freedom of the Hamiltonian, which is a 2-dimensional system, right? Then the codimension of the torus is 0. Wow. What does that mean? Well, it just means the torus itself is the energy surface. Is that surprising? No, that's the pendulum, right? So that's a 1 degree of freedom problem with an elliptic equilibrium point. The torus, which is T1 in that case, is just a circle itself, okay? And it actually coincides with the energy surface, with any energy surface. So whichever, so in this case, there's actually no notable difference between the torus and the energy surface. The torus, which is the circle, is the energy surface. And in fact, the whole problem is to some extent trivial, right? Because if you have a 1 degree of freedom Hamiltonian, then a 1 degree of freedom Hamiltonian, when it has purely imaginary eigenvalues, it turns out it's either positive definite or negative definite. It cannot be indefinite. If it was indefinite, you could not have a center there, all right? So we know, in fact, that in the case of the pendulum, the fact that the Hamiltonian has a minimum there or a maximum and it cannot have anything else, it provides nonlinear stability, and that's no question. So this is basically for bookkeeping purposes only. Let's look at the next case though, n equals 2. So this is a 2 degree of freedom Hamiltonian. So when you have a 2 degree of freedom Hamiltonian, that the dimension of the surviving tori, or actually that's, I already went through that exercise here, that the codimension of the surviving tori from this formula here is what? Is 1, right? Because 2 minus 1 is 1. So if you want to have a picture, then the energy surface is 3-dimensional. So I can think of it as something that I could draw like this, a volume. That's the energy surface of a 2 degree of freedom Hamiltonian. You want an example? Say 2 coupled pendulum, right? That's a 2 degree of freedom Hamiltonian. It's a double pendulum. There's a 2 degree of freedom Hamiltonian. Locally, the energy surface is like a 3-dimensional volume because you fix the energy. So you put yourself in a 3-dimensional volume. And the tori are n-dimensional, excuse me, and n is equal to 2. So that's our usual 2-dimensional torus. So I can draw that with confidence. So I will just draw something like that here. So this figure that I have used symbolically for tori is actually quite valid here. And I know that the surviving tori are 2-dimensional, right? So the surviving torus is T2. So let's talk about stability. Can I guarantee stability? Well, under the isoenergetic non-degeneracy condition, what I have drawn now is valid for any energy surface. So I assume that that's satisfied. Now, what is the implication of that? In a 3-dimensional space, you don't have to care about other energy levels. This exact same thing will be happening on them. A, B, you will never make it there anyway. You're confined to this one forever, all right? So let's not worry about those guys. They will worry about themselves, but then they have the same picture as you do. So you're basically trying to see whether you can escape. There's nothing that would block you a priori. There's no energy sphere if we didn't assume that. And you're trying to see if you can escape. There are all these tori around, and in fact, a whole lot of them. And the key point is that the tori are 2-dimensional surfaces. Just imagine you're inside a 2-dimensional torus. The torus is invariant. You cannot get through. So you cannot get out. So that means that because you have all this abundance of tori, okay, you're stuck. They are nested. It's enough to be in one of them. You're already doomed forever. You can't get out. But in fact, there's a whole lot of them. Right? So by the invariance of these tori, which divide the 3-dimensional phase space into an interior and an exterior, a compact torus, you're boxed in once you're inside a torus. So I need to insert, there's something coming up here that I didn't yet want to show. Add page. Okay. So this means then stability, the Lyapunov stability, that is, because a 2D torus divides 3D energy surface into an interior and an exterior. And both are invariant because the torus itself is invariant, so you can't cross from one to the other. So what's the good news? The good news is that your tippy top, now we understand why it's stable, right? This is the reason why it's stable. So as long as it doesn't have any strong resonance, okay, and it doesn't have a non-degeneracy, two of those. One of them is the regular non-degeneracy and the isoenergetic non-degeneracy, which a generic body would not have. Then there are all these tori through which you cannot get out. So even though your chances don't look good when you first look at the tippy top energy landscape and you say, boy, there's nothing keeping me from here. But it turns out each and every one of those energy surfaces, you're surrounded by tori. It's hard for me to draw that here, but you're stuck, okay? Of course, when you turn on dissipation, we talked about that, so you start drifting downwards. That's another phenomenon, and that's why ultimately the tippy top falls down. But this is the answer. In a perfect world where you didn't have dissipation, it would go on forever. And that's the question we didn't know. Is it because there's some Hamiltonian instability there, or is it the dissipation? And now we can say it's the dissipation, it's not the Hamiltonian part, okay? So a consequence of that is that a non-resonant and I will just say non-degenerate tippy top is non-linearly stable in the absence of dissipation. Okay. What happens, however, when you go to higher dimensions? I mean, the first expectation would be, well, probably the same. And also you could say, also, do I really care? Because I'm not familiar with high dimensional tippy tops. And I told you that what inspired all this investigation was not the tippy top per se, but stability of the solar system, celestial mechanics, where these problems are abundant and have much higher degrees of freedom. So when you have 3 degrees of freedom, then the codimension of the torus, of the surviving torus, is what? Let's use the formula. N is equal to 3. So the codimension of the surviving torus is 2. So if the energy surface is 5-dimensional, I can't draw that. But I will again pretend that it's a volume it's 5-dimensional in the 6-dimensional phase space, all right? So that's not quite right what I'm drawing, but I can do relative dimensions, right? So if this is 5 dimensions, then the dimension of the torus is 2 less. So I have to draw a torus, which in my little cartoon has how many dimensions? 3 minus 2, which is 1. So in this cartoon, the torus would look like simply a circle. So in this picture, this would be T3. My previous picture, it was T2, and it had 1 dimension between it and the energy surface. Here, T3 has 2 codimensions within the energy surface, which creates a big issue because it no longer divides the space. So it no longer makes sense for me to talk about interior or exterior, because a one-dimensional curve doesn't have the ability to divide a three-dimensional space. And likewise, that it has no interior or exterior because the codimension is larger than 1. Okay, so T3, the three-dimensional torus, has the same problem that, funny as it may sound, a three-dimensional torus would still have an interior and exterior in a four-dimensional space, but not in a five-dimensional space. And if you find that mind-boggling, just look at this picture, right? There's no, I mean, this point is not confined. I mean, I can put it there, but nothing will stop that point to wander out because the torus doesn't act as a boundary that it can get around it. Sure, it cannot cross it by invariance, but it can get around it, right? So the thing here is that the conclusion is that the T3 does not divide. You just simply say does not divide the phase space. Actually, not the phase space, but the energy surface. And the full sentence would be doesn't divide into an interior and an exterior, but that we just sometimes say for sure that it doesn't divide, is that trajectories may freely escape. So in fact, the interesting conclusion, which was never seen before in dynamical systems, this kind of two things. It basically is such a strong dimensional dependence that something is okay in one dimension, something okay in 2D, but not in 3. And second, we're not saying that it will escape. It's just that it has the potential to escape, right? So one may just hope that still many of them will stay there, but one cannot exclude the possibility that some will escape. And you know how it goes with instability. If one escapes, that's already instability. So 3 degrees of freedom. And you can imagine things are not going to get better when you increase the dimension further. It will actually just increase the gap between the dimensionality of the two objects. So it will be easier and easier to escape, because the next time around when n is 4, then this will be a 4-dimensional torus, and the energy surface will be 4 times 2, which is 8, minus 1 is 7. So a 4-dimensional torus will try to block things in a 7-dimensional surface. So things are just getting worse as you go to higher dimensions, not better. So 3 degrees of freedom and or let's just say this way, that 3 and higher degree of freedom Hamiltonians or what sometimes people say topologically unstable, which means, let me finish the sentence. If, remember, still, if the Hessian of the Hamiltonian is definite, then even though you can have all these tori and you have all this geometry, you cannot escape because your energy surface is not so friendly, or maybe too friendly. So it keeps you there because it's a sphere. Whereas if that's the definite case, so you can still have all these topological counts and everything. The individual tori will not keep you there anymore, but the energy surface will. So you have topological instability if this d8 squared, the Hessian is not definite. Because if it's definite, you still have the Lyapunov result, but if it's not definite, things can get out. So even if I start anywhere, right, I can possibly, go away after a while. So if that happens, then that has a name to it, that sneak out. And this was first discovered, this possibility, and discussed in examples by Arnold. So it bears his name. So such an, I'll show it on a picture now. So which it goes by the name of Arnold diffusion. Escape in 3 degrees of freedom or higher. So things get really nasty in Hamiltonian systems when you have at least 3 degrees of freedom. That were in fact, I mean, this subject now is fairly well settled, but you know, a few years ago you could see conferences entitled Hamiltonian systems in 3 degrees of freedom or higher. And if you were not an expert and you didn't know what was going on, and you said, why 3? Why not 5, 7, -2, whatever? Why 3? And this was precisely the region because this topological instability can first happen in 3 degrees of freedom, but not in 2D, not for the tippy top, but anything more complicated. So what happens then is that this is hard to draw, and I'm sure I'm going to mess up as I always do, but there are these surviving tori that are nested, and not all of them survive. So there will be gaps among them. The further you go from the origin, the larger the gaps become. So these are the surviving, people call them KM tori for that reason, because these are the ones, they are quasi-periodic. So this is kind of a cut of these, and on these you have the nice surviving quasi-periodic orbits, and on this one too. So on all the surviving ones, but there are these gaps in between. Now, why do we get these gaps in between? We get these gaps because somewhere in the middle of this gap, there was actually a resonant torus. We are moving away from the origin, right? So it's not just a one frequency game anymore. As we move away from the origin, our frequency gets constantly modified depending on where we are. And say at leading order, this actually put me on a strongly resonant torus, which can easily be the case because I only assumed non-resonance for this vector. But if I start moving away in space from the linearized case, then this modulation can easily put me in a strongly resonant case. Now, it turns out those are the ones that get killed off. So you may have had one here, and if it was a strong enough resonance, 1 to 3, 1 to 4, whatever, it actually causes the normal form, the normal form transformation. You can do formally the normal form transformation at each step, but it will not converge. And the non-convergence will happen not just along that torus, but actually in a sizable neighborhood of that torus. So this is what the gaps are due to. Now, higher order resonances also matter because it's only the quasi-periodic tori that survive, but the higher order resonances will have smaller gaps associated with them. So it's all about clearly, see, the diffusion, if it happens, this Arnold diffusion, which is this topological instability, it cannot happen on the surviving tori because we know what they do. They just do this forever, right? So something funny must be going on here in these gaps. And indeed, in these gaps, you can have incredibly complicated dynamics. First of all, the building blocks of that dynamics are the remnants of the resonant torus. The resonant torus has surviving individual lower dimensional tori. So that was, say, an n-dimensional torus. It has broken down into an n-1 dimensional torus or n-2 dimensional tori. In this case, this was the torus, whatever the dimension of that had, right? And the full dimension was, in my picture, 2, and now it's breaking down to 1. So, of course, this continues in both directions. It doesn't end there. But the reason I'm showing a dot there, because I will set up a point, I I will talk about a Poincare map here that will keep mapping. It will be sort of a first return map that I set up here, perhaps in some different color, within the energy surface, if it lets me do that. Not for now. So this would be a first return map. Transfers to the tori. And you imagine what happens if I start on a torus, right? So if I start on a torus, then I do this thing and I come back and we'll land somewhere else on the torus. In the gaps, the same for the other torus. In the gaps, it's anybody's guess what I'm going to be doing, but there will be some anchor points in the gaps, and those will be then these lower dimensional tori. In my current picture, it's a fixed point. Say here. So let me say what those are. Lower dimensional tori. You may have any number of these depending on the resonance. So this would actually correspond to a 1 to 2 resonance. And the way you would move under one iteration of the Poincare map is that you would, leave around 1 and then come back and intersect here. And the next time when you come back, how do I show that you come back here? So this would actually correspond to, if this is the particular gap and this is the gap dynamics, this would be a 1-2 resonance in this picture. Which means that I used to have a whole torus of such trajectories that did exactly what I'm doing now, but all of those basically got killed off, and I just have a discrete one that does this. That second time around it comes back. That's not the full story. This is actually an unstable set of tori. Which shows up in the following way in the Poincare map, that you would in fact have stable and unstable manifolds associated with them. Let me firm these up. So I'm showing now these invariant sets for the Poincare map. And believe it or not, they tend to interact with each other like this, the way we've seen when we studied chaotic dynamics in simpler systems. This is what I'm showing for the Poincare map. They will generically intersect transversely, like so. And if they do that, we know what will happen. You will have homoclinic tangles right there, chaotic dynamics in the gaps. Small scale chaotic dynamics. So these will be, you could view them as heteroclinic tangles, but it's really just the same torus repeating itself. So these are homoclinic tangles. So you have a chaos in the gaps generically. And that's not the full story, because there's also more happening here, and in a different color. Here in these regions, just as you would have in a heteroclinic, in the middle of the heteroclinic cycle, there will be actually another pair, in case of a 1 to 2 resonance, surviving lower dimensional tori, which are then elliptic in nature. So again, the way to imagine these guys is that, again, you start from here, go around, hit the other one, go around for the next time you come back here. So this is also a period 2 orbit in my picture. It will be a higher dimensional torus in the general setting. But unlike this one, which was unstable, this one is stable. Or is it? Well, I didn't say it's stable, it's elliptic. So amazingly, here's another amazing thing in this dynamics, that look at this picture. That picture would be a microcosm of the large picture. Within that set, again, you will have a bunch of those tori which are here, sticking out of it. A bunch of them will be surviving, but you will have gaps in between. And when you look at those gaps, you will see the same structure repeating endlessly. So there's a fascinating self-similarity here that numerically you can only explore to some extent, but you are guaranteed to have this, that it will be just repeating itself. So these will be this will be elliptic, lower dimensional elliptic tori. And then you will have gaps in between. And then blah, 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 and you see self-similarity. So this is an incredibly complicated, fascinating picture. This will happen in each and every gap. So it will happen here, okay? And not only in each and every gap, but also will happen on each and every energy surface, even if you're stable. So even if you have a double pendulum, which has a minimum for the Hamiltonian at this position, if you apply small perturbations, then in the small, on a microscopic scale, all this will be taking place, except that you will not be able to get out because of topological constraints, but you're stuck in between the gaps, and you do this forever, chaotic dynamics in between the gaps. Now, what's Arnold diffusion? Arnold diffusion is when you don't have that energy surface grabbing you. So that is the case when you have for indefinite because then all this mess that you have in the gap can actually aid you in your wandering. This is in fact the mechanism that helps you wander around, this chaotic dynamics, because these guys are not the ones that will either participate in instability or help you, because they just do their thing. They also keep coming back. But everything else, especially in this chaotic dynamics, so the mechanism for instability that Arnold identified, and he called it diffusion because it's slow, it would be called transition chains formed by heteroclinic connections, also homoclinic connections among lower dimensional, the term is hyperbolic tori, or some call them whiskered tori, perhaps for obvious reasons, because these are like whiskers, or something that these are like whiskers. This has become actually a standard term, whiskered tori. So that's a fascinating subject, but I just give you the idea that basically here's one of those little hyperbolic tori. Again, don't sweat the actual geometry. I just refer to it as a point, and it may have a connection with another one, because in all this mess, everybody's stable and unstable manifold will ultimately intersect everybody else's. So this is one torus. This is another torus, lower dimensional, and there's several of them in these channels. Now, they're not separated from each other because, unlike my picture suggests that once you're in one gap, you cannot get to the other, because that's the limitation of how I can draw. But in the case when you have 3 degrees or more, these gaps are not separated from each other. Why? Because there's no interior, no exterior anymore. If you started out in one gap, so to speak, it's like a tunnel system. You can get into the other one. But the question is, what propels you? Because you need propellants to start getting out, right? This is your direction of instability. Moving in this direction is not by itself, is not getting out. But, have one mess in this one of the gaps, and then you have the mess in the other gap. And since they are not separated from each other, sooner or later, these manifolds can find each other and intersect. And if you have several of these, so these are all tori, with their own intersecting stable and unstable manifolds like that, then the sort of the naive picture is that, okay, now look at what this one does, because it starts doing this, sooner or later will intersect this one, which was there. And since this one was doing the tangling, right? And this is doing the tangling, sooner or later intersects that one. So this is true across the board. And when you have this chain of intersecting trajectories, you can actually prove that there will be trajectories that are traveling nearby along the whole chain. So this will be the diffusing or escaping trajectory. Nearby. And this is called a transition chain. Now, some of this is still not entirely completely mathematically rigorously cleaned up, but most of it is, and people have seen it also numerically, because the high precision simulation shows that this is the case. But this is an incredibly hard problem. First of all, Arnold showed a model. He didn't prove it. He didn't manage to prove it for the actual setting, but he set up a model that had that. And then people went to the actual setting of a perturbed Hamiltonian system. And with a lot of work, they showed that to be the case. This is not a simple Melnikov method. These splittings here turn out to be exponentially small. They are beyond the reach of the Melnikov method, interestingly, but they do happen. The diffusion turns out to be exponentially small because the splitting is exponentially small. Exponentially slow, I should say. But it does take place. And that's actually a theorem by Nekhoroshev. I wrote it out in a bit more detail in the text, and I'll show you what this picture is in a second. So under further non-degeneracy conditions, you do get the diffusion. It's exponentially small, but it takes place. This is a picture of such a Poincare map. So the simplest model for such a Poincare map for a 2 degree of freedom system, it has the dimensionality that I'm showing here. Because in 2 degrees of freedom, the torus is 2-dimensional, energy surface is 3-dimensional, and you can set up a 2-dimensional trap, Poincare map, within the energy surface to see this. There's no diffusion in 2 dimensions, but at least you get an idea of the nature of the picture. And the best sort of a classic model for that is a discretized version of the dynamics. See, think of this as, this is sort of the r dot equals 0 would be the r dot equals 0 and phi dot equals just omega plus order r. That was our leading order dynamics. So we have the omega plus order r here because, in fact, what you have here in terms of a discrete mapping, in terms of a discrete mapping, you just you have an order r modulation to what you would have normally, just a stepping in phi. And here, instead of having a constant r, which would be just rn plus 1 equals rn, you have now a coupling term which brings in the phi dependence. And that would be something that you cannot remove because you had a resonance there. Remember, we were able to remove from this equation the coupling term to begin with here. There was no coupling term because the normal form transformation was able to clean out the phi dependence from this part. To that, at this level, we needed a non-resonance condition. If we have a resonance, we cannot clean that out. So what would be the simplest case? The simplest case is you put some function of phi there. The simplest one. It has to be periodic. So that's what the standard map does, right? At the level of a map. So that's why this is a model, a first order model for what happens within a resonance. So this is already a model for what happens within the resonance, but also you can just, since I said you have self-similarity, you can just take it as an overall model for what happens to Km tori. So just imagine, think of this as a fixed point. And the statement is that many of them survive, most of the tori survive. Well, the most becomes actually less and less as you move away. And see what happens when I blow this up. This is a numerical picture of the iterations. The colors here just mean different initial conditions. So they take an initial condition and the iterates of that have the same color. So see, when I blow this up, numerics cannot show you everything because the gaps are still small. But look at, this was a resonance here. See, somewhere here there was a resonant torus. And that got broken down. And these are those elliptic islands that are created out of that resonance. And then there are the hyperbolic points somewhere here. And again, there will be generally a heteroclinic tangle connecting them, but its exponential is very small, so numerics cannot resolve it at this level. When you then take a bigger picture view of this and they say, oh, this is actually what's happening inside of resonance, because the model for that, then you see that the numerics can resolve it better here for a larger torus that has all these islands. And here you had the hyperbolic fixed points. And all of a sudden, you don't see such a nice clear-cut connection by the colors between the two. Reason being because here you have the tangles now. That's why you have all blue here, because it's a mixing region. And the beauty of this, again, is I was looking for instances of that. This is already happening. This is an elliptic region created inside the resonance. But here's the self-similarity, that in this elliptic region created inside the resonance, there's further tiny elliptic regions, right? And then if you had the ability to go into that, you would see further tiny elliptic regions there. So this is a sort of a beautiful representative picture. One last thing, sorry, because I just on that note, evidence for Arnold diffusion. Since it happens, it takes long time scales and it requires a near conservative dynamics. So you cannot have substantial dissipation. People had to go back to the original source of the problem, celestial mechanics. And in celestial mechanics, people think that the most striking example of what they think is Arnold diffusion is the asteroid structures near planets that have these rings of asteroids, for Saturn's or Jupiter. And we are so much used to popular illustrations of this, we don't even ask, what are those? So we see layers in those rings. Why? Because normally it should be homogeneous. What are those? Those are little, celestial bodies, rocks, pieces of rock. Okay. Over the years, they should fill up these regions over the not years, millions of years, uniformly. Why not? Well, the reason why we see these stripes there is that there are gaps in this. And the reason why there are gaps here, and this was discovered by somebody named Kirkwood, and now it's proven that it exists for all these planets that have asteroid belts around them, is that at certain distances, the orbiting angular velocity around Jupiter for those particular asteroids, which is the period of the frequency, which is actually a function of the distance with the semi-major axis of these, because they all move on ellipses. So you can either think in terms of their period or frequency, or you can think of their semi-major axis, which is another way to parameterize their frequency. In any case, their orbital frequency around Jupiter is in resonance with the orbital frequency of Jupiter around the sun. So this is a dynamical system which has both frequencies in it, all right? And it's a Hamiltonian system. And at these points, there's a 3-to-1 resonance between them. For instance, here there's a 5-to-2 and so on. And the point is that, of course, originally, there was no reason why these should be depleted, these regions, but people think that they are depleted now. What you see here now is the number of asteroids here, and see how it goes down in those regions. People believe that that's happened over whatever millions of years, because those celestial bodies, these pieces of rocks, the asteroids, have escaped from there. So they got propelled out by the resonance and by diffusion. If there's a lower dimensional problem, even though there were resonance gaps, they couldn't leave. The reason is here. They're still stuck in there forever. But this is a higher dimensional problem, because you have the little body, you have Jupiter, and you have the other bodies, and the whole thing is in the solar system, right? So it's a multi-degree of freedom problem, no matter which way you look at it. But the dominant resonance is the one that drives you out of there, the resonance between Jupiter's own period and the period of those. And this is really a spectacular indication that over millions of years, Arnold diffusion takes these celestial bodies out, and that's why you have practically none in those gaps. So sorry, I'll give you this time back tomorrow. I took extra 5 minutes. But that's what I wanted to say today. And then with that, I'll just finish the Hamiltonian part. Any questions? So I'll just say this here, what it is. This is evidence for Arnold diffusion. In the solar system. And these are called Kirkwood gaps, but not just in the context of Jupiter, but also for Saturn. This is a general phenomenon. They have been documented and well observed for other planets as well. Okay, and this is sort of the internal structure of gaps among tori. Okay, any questions? Have I done such a fantastic job explaining this incredibly complicated phenomenon that nobody has any question? I'm really impressed with myself. Never managed to do that before. See, I'm getting really good here, really good. That's probably not the case, right? To be honest with you, like I said, I didn't appreciate, for instance, the isoenergetic non-degeneracy condition. I owe you a confession. In my master's, what is it, thesis, I actually did look at the tippy top, and I actually did compute all the conditions except for the isoenergetic non-degeneracy condition, because there were accounts that by other people, I guess books, that also didn't understand the significance of that. So I did do these tremendous normal form computations and went through actually to prove the stability of a more general gyroscopic problem, which is a fast rotating shaft with an eccentric disk, which is basically turbines over their critical speed. The turbines over the critical speed are nominally neutrally stable, okay? But the energy, the Hamiltonian that would describe them without dissipation doesn't have a minimum there. It's this classic problem of a gyroscopic system. So the question is that, are they without dissipation? Are they stable or unstable? And I dutifully calculate the normal form, non-degeneracy condition, non-resonant graphs and everything. And that isoenergetic non-degeneracy condition, I had no idea what that was all about. And some of the books that I read about, they didn't talk about it. And I thought, okay, I'm not checking that one. So my confession is that I never checked that one. And I still claimed that the shaft was stable. Of course, I did do numerical simulations. It did seem like it was stable. But of course, if Arnold was alive, he passed away, unfortunately, what, good 10, 15 years ago, he would nail people on this. Somebody said, it seems like there's no Arnold diffusion. Then if he was in the audience, he would stand up and say, how would you know that? And I said, well, we don't see it. Well, it doesn't mean anything because it takes exponentially long time, right? So just because you ran your numerics for a few hours, it doesn't mean anything. So he himself would nail people on that. But that's just sort of an anecdote. But later on, I realized the significance of that. That's what graduate school is for, that you get deeper into things and then you sit down and you don't rely on other people's explanations anymore, but you really try to discover it yourself. And then you can get amazingly deep when you have all the time of the world, well, at least the longer time. Anyway,
I might just have one question regarding the Arnold diffusion.
Okay, go ahead, Alex.
That's a fast one. Is there any connection between random walk theory and the Arnold diffusion? Because as I recall from random walk theory, in 2 dimensions there is one, so the probability of coming back is 1, whereas in 3 dimensions the probability of coming back is definitely lower than 1. And the same analogy applies here.
I'm sure that there's a dimensional connection. the random walk, basically it has a very particular distribution. I don't know, say, in a discretized form, it would be a Brownian discretization of a Brownian motion. I don't know personally, but I'm not an expert in this area. I don't follow this on a daily level, but I don't know any work that would describe that, how this would be related to, but very likely. I mean, what you're saying is very likely, so it could be. Because there's randomness involved here, no question, right? So we understand the reason why I'm hesitant is that what we strictly know is that we know what homoclinic chaos is, what symbolic dynamics is, and so on. But I'm not enough of an expert in that area that I would know whether somebody specifically, investigated.
Yeah, basically the same thing applies, or it is a similar difference between a 2D and the 3D case.
Oh, you mean that? So you don't necessarily look at random walks here?
No, yeah, I mean, in random walk theory, it's specific there because, like in 2D, you're guaranteed to come back if you wait long enough.
Yeah, but see, then now that you say that here, it's more of a topological thing, right? So what here creates an opportunity for you to get out is that all of a sudden something that used to be a barrier in lower dimensions is no longer a barrier. So that's why people refer to it as a topological instability. You can still have chaos in 2 degrees of freedom, but you don't get out. So now that when I think about it, I'm not convinced that there is a connection for that reason, because here it's purely a dimensional barrier, but there could be. I don't know. That's interesting to look at. Okay, anything else? Okay, so I'm done with Hamiltonian systems. If you have any more questions, you can ask them tomorrow. But what I'd like to do is move on to the next big subject, which is invariant manifold theory in higher dimensions, right? And you already see that invariant manifolds, stable, unstable manifolds come up in all sorts of settings, but we have only been able to handle them if they are like this, say at a low dimensional. In this case, I can only draw them if they're low dimensional. But they're incredibly important in higher dimensional systems as well. So there's a general theory for them, for the ones that really matter because they are robust, and that's what I want to start talking about tomorrow. So no more questions, then have a good evening. See you tomorrow.